The Chengdu J-20 Mighty Dragon's operational capability is fundamentally predicated on a deeply integrated and synergistic relationship between its advanced sensor suite, its networked battle management systems, and its diverse arsenal of weapons, all housed within a very low observable airframe designed for long-range, persistent operations in highly contested environments. The core of this capability is its sophisticated active electronically scanned array radar, a system that has evolved through multiple generations of technological refinement. This AESA radar is composed of a dense grid of thousands of individual transmit-receive modules, each acting as a miniature, independent radar. This distributed architecture allows for the generation of numerous highly directional, pencil-like beams that can be electronically steered across a wide field of regard at the speed of light, with no inertia or physical movement. This near-instantaneous beam agility is the foundational element that enables the system's multi-functionality, permitting the concurrent execution of disparate tasks. These tasks include long-range search using complex velocity and raster scan patterns, high-priority track on multiple airborne and surface targets with fire control quality update rates, high-resolution synthetic aperture radar mapping for detailed ground imagery and target identification, Doppler beam sharpening for real-time ground mapping, terrain following and terrain avoidance flight profiles for low-altitude penetration, and dedicated electronic support and electronic attack functions, all interleaved within a single, dynamically managed radar timeline controlled by an intelligent resource manager scheduler. The performance of this radar system is intrinsically linked to breakthroughs in wide bandgap semiconductor technology, particularly the adoption of gallium nitride for the power amplifiers within each transmit-receive module. GaN semiconductors offer a superior combination of high breakdown electric field, high electron saturation velocity, and excellent thermal conductivity compared to previous gallium arsenide technology. This translates directly to the ability of each module to operate at significantly higher power densities, collectively enhancing the entire array's effective radiated power, which is a key determinant of detection range, especially against radar cross-section optimized targets. The higher operating voltage of GaN reduces current requirements and associated resistive losses, improving overall electrical efficiency. To manage the substantial waste heat generated by thousands of these high-power modules operating simultaneously, the system relies on a sophisticated thermal management system, almost certainly employing a liquid-cooled cold plate in direct contact with the array's backing structure. This system uses specialized coolants with high thermal capacity to transport heat to advanced heat exchangers, likely integrated with the aircraft's environmental control system, ensuring all components remain within their strict operational temperature envelope to prevent performance degradation. Underpinning this hardware is an immensely powerful and complex signal processing architecture. The raw data from the array is processed by a heterogeneous computing architecture combining general-purpose processors, digital signal processors, field-programmable gate arrays, and application-specific integrated circuits optimized for specific radar functions. The processing chain begins with high-speed, high-resolution analog-to-digital converters that capture the radar returns, which then undergo real-time digital beamforming. This creates the multiple, simultaneous, and independent beams essential for the radar's multi-role capability. Advanced algorithms, such as space-time adaptive processing, are computationally intensive but are crucial for discriminating slow-moving targets from heavy ground clutter. For tracking, advanced nonlinear filters like the interacting multiple model and probabilistic data association filters are employed to maintain tracks on highly maneuverable targets and resolve measurements in dense multi-target environments. The system's constant false alarm rate management is adaptive, learning the background clutter and jamming environment to dynamically adjust detection thresholds. The tracking system employs multiple hypothesis testing to evaluate potential target paths, allowing it to reject sophisticated deception jamming and maintain track continuity. This radar does not operate in isolation but is the primary node in an integrated sensor suite. It is seamlessly fused with an infrared search and track system, which provides passive, long-range detection and tracking in multiple infrared bands, an electro-optical targeting system that combines high-resolution television cameras, mid-wave infrared sensors, and laser designators, and a comprehensive suite of electronic support measures for detecting, identifying, and geolocating radio frequency emissions. Sensor fusion occurs within a high-bandwidth integrated core processor, which runs complex correlation and association algorithms to combine the kinematic and attribute data from all sensors into a single, coherent, and identified track for each object in the battlespace. This process enables automatic cross-cueing. For example, a tentative radar detection at extreme range can slave the IRST system to that bearing for passive confirmation, preserving the aircraft's electromagnetic silence. The fusion architecture increasingly incorporates machine learning models for automatic target recognition, classifying targets based on their radar signature, infrared profile, and electronic emissions, thereby reducing pilot cognitive load. The system's electronic warfare capabilities are deeply embedded and multifaceted. Beyond its primary sensing role, the AESA can function as a high-power, highly directional jammer. Its ability to form multiple, independent beams allows it to conduct electronic attack against several threats simultaneously, such as disrupting the fire control radar of an approaching fighter while also degrading the seeker of a surface-to-air missile, all while continuing to track all targets. Its electronic attack repertoire includes complex deception jamming techniques like range gate pull-off and velocity gate pull-off, as well as the generation of digitally synthesized false targets with realistic radar cross-section fluctuations and motion characteristics. The system's low probability of intercept and low probability of exploitation characteristics are enhanced through complex waveform diversity, including ultra-fast frequency hopping, wideband chirp modulation, and polyphase-coded waveforms that make its emissions appear as low-level background noise to hostile interception systems. This unparalleled situational awareness is leveraged by the J-20's integrated weapons systems, which are carried primarily in internal bays to preserve its stealth characteristics. The main ventral weapons bay is configured to carry multiple long-range, beyond visual range air-to-air missiles. The primary weapon in this category is the PL-15, which features an active radar seeker, a dual-pulse rocket motor for extended kinematic range, and a two-way data link that allows it to receive mid-course guidance updates from the J-20's radar or other networked platforms. This combination enables the J-20 to engage high-value targets like airborne early warning and control aircraft and aerial refueling tankers at very long distances, a cornerstone of the counter-intervention strategy. The two smaller lateral weapons bays, located on either side of the fuselage, are typically equipped with short-range, infrared homing air-to-air missiles like the PL-10. The PL-10 incorporates an advanced imaging infrared seeker and thrust vectoring control, granting it an exceptionally high off-boresight capability, meaning it can engage targets at wide angles from the aircraft's nose. These missiles are integrated with the pilot's helmet-mounted display system, allowing the pilot to designate targets simply by looking at them. For air-to-surface missions, the J-20's ventral bay can be reconfigured to carry various precision-guided munitions, including satellite-guided bombs and smaller-diameter glide weapons, enabling it to conduct strikes against heavily defended fixed and mobile targets. The aircraft's sophisticated sensor suite, particularly its high-resolution SAR mapping and EOTS, provides the precise targeting data required for these weapons. The J-20's design also includes provisions for carrying additional weapons on external pylons, though this significantly increases its radar cross-section. This beast mode configuration sacrifices stealth for a massive increase in payload, suitable for environments where air superiority has been established or when confronting a large number of threats. Network integration is the final, critical piece that binds these capabilities together. Secure, high data rate, anti-jam tactical data links allow the J-20 to function as a node in a larger combat network. It can share its detailed sensor picture in near real-time with other J-20s, surface-to-air missile sites, naval vessels, and command centers, contributing to a common operational picture. Conversely, it can receive targeting data from off-board sensors, such as other aircraft, satellites, or unmanned aerial vehicles. This enables advanced cooperative engagement concepts, such as silent launch, where one J-20 can guide a PL-15 launched by a wingman without ever activating its own radar, or where the aircraft can launch a missile based solely on targeting information provided by an external source. The entire system is designed with a modular, open systems architecture to facilitate continuous technology refresh and capability upgrades throughout the airframe's service life, ensuring it can adapt to counter emerging threats and leverage new technologies in the relentless evolution of aerial warfare.